right, let's get started. Today we're going to continue the discussion about the design of experiments, and we will be looking at one case study in great detail. One of the original field trials that was designed about 50 years ago, and a lot of the elements of the design of this field trial became the status quo for clinical trials in medical practices since then. We will also be looking at how medicine has changed somewhat, and that although these standards were adopted 50 years ago, they're still really difficult standards to adhere to. And from there, we will move into trying to dissect this field trial in terms of what are the features in design of experiments that were used in this particular field trial and why they were used. Okay, so this is about polio. And the first cases of polio were in the early 1900s, 19-teens. And the polio affected children the greatest, young children in sort of first through third grades. And many children from when polio first hit the United States until this vaccine was tested, hundreds of thousands of children died from polio, and those who did not die often were crippled or could only survive in respirators. So there were several different groups of people working on trying to find a vaccine for polio, and Jonas Salk's vaccine seemed to be the most promising in the laboratory setting. But they really needed a large field trial in order to see whether or not there were adverse effects to the point where they would not want to administer it to all children. So there was a decision to have a field trial that was going to be on large scale, basically larger than any other field trial ever before. And it was going to be a year-long trial in 1954. Tommy Francis, who was the advisor or mentor for Jonas Salk, was asked to design the field trial. So it involved nearly 2 million children from 217 different areas across, mostly in the United States, but across the United States, Canada, and Finland, and cost $17.5 million.
Today's money or?
That was $1954, so it was extremely expensive. There was a lot of publicity about this trial. Here's a picture of Jonas Salk administering the polio vaccine, and it was on the front cover of Time magazine. Again, this is from Life magazine. Salk is in the center here, and on the left is Tommy Francis, who was the professor at the University of Michigan, who trained Salk, who then was brought back to design the field trial. All right, so here are some considerations that needed to go into how you would design this field trial. The first one is that polio, although the incidence of polio was on the rise, it was not a increase from one year to the next necessarily. In other words, there were some ebbs and flows because it's such a highly contagious disease. It also was found that it affected poorer children at a lower rate than children from higher income families. So it was thought that the reason why this happened is because the poorer children often caught the polio at a much younger age when they still had the antibodies of their mother, and then they were able to then develop antibodies themselves to fight polio, and so there was a lower incidence of polio at the among children that were in this sort of 6 to 8 year old or 6 to 10 year old group. And when the children caught it at a much younger age, because they had their mother's antibodies, it was not as severe a case, and so did not result in sort of crippling and the other terrible things. So it's also, as I've mentioned already, highly contagious, and so the infections of polio tended to sort of clump. And here are the here's the data dating back from 1930 of the number of cases of polio from 1930 to 1956. And so you can see, although in general it's on the rise, there are dips and little rises and dips as we go along. So when they're trying to design this field trial, they have to be careful in that since there are decreases from one year to the next, they need to know if a decrease when in the year that they were administering it, is that decrease simply due to the normal fluctuations in the incidence of polio, or is it due to the actual vaccine itself? So they had to figure out a way to make sure that they were going to guard against making an improper conclusion if there were a decrease as to whether or not this is as you can see, from 1952, there's a huge number of cases, nearly 60,000 cases, and then to 1953, the number of cases dropped. If you even look at 1954, there were more cases in 1954 than in 1953. And in 1954 was when they did the field trial of the the polio vaccine. And so simply going by these numbers alone, you might get a misleading conclusion, because in fact this polio vaccine was found to be extremely effective, and we all still, well, do you guys still get it? You do, right? No? Has polio now been considered eradicated and you no longer need to get the polio? You do, right? I can't, you think you got it? Nobody remember? Well, you would have been like 3 months old when you got it, so, and then 9 months old, so you might not remember. Yes?
Yeah,
you still get it. Thank you. I should know this too. I've got kids your age, but I can't quite. They had so many vaccines, I can't quite remember. Okay, so finding a comparison group. So it's important to figure out if there's the group that's been treated has a lower rate of polio or not. And so you want to be able to have another group that you can compare it to where the other group did not receive the vaccine. So there's some complications here, and this gets to the ethics of clinical trials and field trials. There's a complication is that you can't simply go up to everybody in this classroom and say, I'm trying out this new vaccine and you're all subjects in it, and I'm going to give you a shot. So you need to have consent, that someone's willing to participate in the trial. And given that these are children, you need the parents to consent. So I have a question for you here, which is, how about for the comparison group, we use the children whose parents did not consent. So the ones who consented, we give them the vaccine. The ones whose parents did not consent will be our control group that we're going to compare the incidence of polio among those whose parents did not consent versus the ones who did consent. So that would be a comparison group. What do you think of that? Are there any problems with that? There's no double blind? What does that mean? Mm-hmm.
You're not compensating for the placebo effect.
Right. Your jump. That's true. If yes, that's true. If you did not consent, then you're not getting any kind of vaccine at all, even a fake vaccine. There's even a more fundamental problem with it than that. We're going to get to that as another example. So hold that for a second. Yes. That's exactly right. So the statement was, is it possible that there's a very fundamental difference between the parents who are likely to consent and those who do not? So could there be some difference that would then affect the also affect the rate at which they might get polio? And the suggestion was, are poorer people less likely to consent or more likely to consent than higher income people? And that's generally the case, is that higher income people tend to be more likely to be willing to participate in a field trial. And so what about income? What difference, why did you pick income? It's like there are only very few things that I mentioned on the previous page, and income was one of them. So there were two, in fact, designs created, and I've been reading a little bit on this, and there are conflicting reasons that I've seen as to why there were two designs. One reason that was put forward in one of the sources that I read was that politically they needed to have these two different designs, and so it wasn't simply a decision based on the scientific method, but it was also a decision based on what would fly among the population. And here's one of the designs, which was that only second graders would be vaccinated. And not all second graders again, but only second graders whose parents consented. And then the first graders and the third graders would act as controls. So these are called sort of observed controls, in the sense that you're not actually choosing who's, you get somebody and you say, you're going to be a control. It's more by the fact that you are in first grade or third grade, you are a control. And this method was used in about half of the 217 different study areas. So what little information I've already given you about how polio spreads and who gets it, can you think of a couple problems with this design? Yes?
Well, if the vaccinated kids are all hanging out together and the non-vaccinated kids are hanging out together, it's not really representative of what it would look like if the vaccinated population was still exposed to non-vaccinated people who are supposedly more likely to get disease.
Yes, so you're tapping into the question or the characteristic of it being a very highly contagious disease. And so if the folks who are, or the children who in first grade and third grade are all, none of them are vaccinated, whereas the second grade is sort of a mixture of vaccinated and not vaccinated children, then what if the epidemic that year in some of the schools hit one grade more than another, which you could imagine might happen because it's so infectious. And so then that could go in one direction or the other. If it hit the first graders harder than the second graders, that might make the vaccine look more effective than if it hit the second graders harder than the first graders. So it is possible. You can imagine that that something like that could happen, where a particular class grade level of students might get hit harder with the polio than another. And the fact that we are using grade level as a way to create our control group and our treatment group could then be mixed up with the results. There's another reason why this is not such a good plan. So there are two. That's one of them. What's another one? Yes? Mm-hmm. In the earlier on when they were younger? Is that what you're thinking? Yes, that's true. That's kind of connected to what Manisha was saying, I think. But it's, yes, if there's clumping, then the fact that we've clumped them by grade level might be problematic. There's still one more issue. Think in terms of this issue of consent and non-consent. That's not what you were going to say? How are these two groups different in terms of consent and non-consenters, which we've already identified as a potential problem?
Consenters be a lot smaller in proportion to the non-consenters because you have two grade levels. Or do they control it?
It is the case that grades 1 and 3, you're using all of everybody, and therefore there'll be more children in those groups. However, these groups are so huge that that's not an issue. But that's connected with what's going on, not size, but yes?
Would the first and third graders have some non-consenters in the control?
Right. So the point is you're using all first and third graders. So if you were to go to the parents of first and third graders and say, do you consent to this or not, then the first and third graders would be split into the children of parents who consented and those who do not. We're lumping them all together. And so that's saying that there'll be a different economic mix of children in the first and third graders than there will be among the second graders whose parents consented. And so that gets us back into that same issue of then income. These two groups could look different according to family income, and we know that family income is connected with the incidence of polio. And so that further complicates things. All right, so the other design used a random assignment, and this dates back to the ideas that were first introduced by Fisher, which we saw on Monday, this notion of randomizing. So that's a careful application of some sort of chance process that gives, so instead of using non-consenters as our control group, we take all the children who have consented, whose parents have consented. And of those, we would randomly assign them to treatment or control. So the idea is that this random assignment is going to mix the children up well enough such that roughly those who are getting the vaccine and those who do not, if we look at all different types of characteristics that we're concerned about in terms of the rate at which they might contract polio, will be roughly the same. So randomization is a sort of leveling process that we get to use such that there might be other factors. I've only given you one, so the idea of income, but there might be many other factors. Hygiene is another one. Children who grow up in a very, very clean environment were actually more susceptible to polio than those who grew up in a less hygienic environment. And that, again, is because they contracted polio at an earlier age. So there could be other factors that we're not even thinking about or don't even know about, and they could affect the outcome in terms of whether or not the child gets polio or not. And this randomization process sort of divvies them up equally between the two groups, roughly equally. Okay, so Warren, this gets to your point. This is the notion of placebo controls, which is even when the children are not getting the actual vaccine, we still give them a shot. And that shot is a saline solution. Why do we do that? I think, Warren, you were suggesting a few reasons. Why would you bother to do that? I mean, why would you do that?
The idea that you're getting medicine makes you feel better. It actually helps pregnancy.
That's true. It's often it's found that just the fact of taking a pill or being attended to by a doctor makes you feel better or can improve your situation. And so this is a way of leveling that difference by giving everybody a shot. So, and there's more to it, right? Not only do you have to give them the pill, or shot or whatever, but what else do you have to do? What else goes hand in hand with giving them the fake medicine? If you said, hey, yes?
So they don't know whether the control or
you don't want them to know that you're giving them the fake medicine. So if you say, oh, don't worry, this is just a salt solution, then they're going to know that they got a salt solution and they didn't get the real drug. And so you want the parents and the children to not know whether or not they got the real drug. So again, that's part of the consent, is that they have to know that they might get randomized into the control group and therefore not get the vaccine, or randomized into the treatment group and therefore get the vaccine. The behavior of the parents could be different if they knew that their child did not get the vaccine. They could be much more vigilant, worried about whether or not their child is getting coming down with polio, and make different decisions about the treatment of the child if they start to look sick. In addition to that, there are borderline cases of polio. And if the physician knew whether or not the child had received the saline solution or the actual vaccine, that might affect his or her determination of whether or not they actually got polio. So the physician's not told either. And so the evaluator is also blind. So this is called double blind because the subject, which is the parent and the child, do not know whether or not they have the saline solution, the actual vaccine. And the evaluator, who's making the measurements, determining whether or not the child contracted polio or not, they also don't know which children received the vaccine and which did not. So in essence, this is a randomized placebo, double-blind, controlled experiment. So we randomly assign the treatment to children, and this method was used in roughly the other half the area, study areas. All right, so here's the data. Hopefully you can all see it. Why don't you just concentrate on the total polio cases. Now these total polio cases are being reported per 100,000 children. The reason why it's per 100,000 children is so when we've got a really large group, like this control group of 725,000, that this 54 is per 100,000. It's not in 725,000, so that we can make direct comparisons between groups, even though they've got a different number of children in them. So it's like percentages, except the percentages would be so small. So in a way, a percentage is per 100 children. And instead, we're doing something per 100,000 so that we can deal with numbers that are sort of like integer numbers. So let's take a look at each of these numbers. So the placebo control area, meaning the randomized experiment, double-blind controlled experiment, had 750,000 participants. And of those, roughly 400,000 consented, and they were split into two groups, the vaccinated group and the placebo group, roughly 50-50, so roughly 200,000 in each. Of the vaccinated group, there were 28 cases of polio per 100,000 children. Of the placebo group, there were 71 cases of polio per 100,000 children. Then of the observed control group, meaning the first and third graders were the controls, and the second grade consenters received the treatment. We had about 1 million children in this area. 221,000, or nearly 222,000, received the vaccine, and there were 25 cases per 100,000, versus the control had 54 cases per 100,000 children. So I want to focus on two pairs of numbers. Let's compare the incidence of polio between a control group and a vaccinated group for each of the two studies. So which one of those two studies, those two different approaches for assigning children to control and treatment, so which of these two designs has a bigger impact, shows a bigger impact of the vaccine? The what? In the placebo group? So you're saying that, why? Because I would say, well, look, there's actually a lower incidence of polio among the observed control group. There were only 25 cases per 100,000, as opposed to the placebo control group where there were 28 cases per 100,000. I'm just being a devil's advocate. In fact, you're correct. But why? Yeah? Mm-hmm. Well, or they could differ by the reasons that we described already. So, yes, we want to be making the comparison. That's it. That's the key thing. We want to be making comparisons. And what's the appropriate comparison here is the control group versus a treatment group. And we see a much bigger difference between in the placebo control area, where the placebo group, their incidence was 71 per 100,000 versus the vaccinated group was 28. So that's a very big difference of about 40, more than 40 cases per 100,000, whereas in the observed, the difference is about 30 cases per 100,000. So why is it, why would that happen? Why would it be, if we relate back to the few things that we've talked about in terms of how polio spreads and who contracts polio, why might this not be such a surprise to you? Yes? A question? Uh-huh.
So the two who got the salt solution, couldn't they just have like a false sense of security that they were vaccinated, and as a result the behavior would be less careful in contracting polio?
Yes, that's right. The people who, well, they might be more careful, and
They would be less careful because they thought that they would have the vaccine.
okay. Yes, that's true. That could happen.
So in a way, we don't really know if that way is more effective, because if people who don't have the vaccine, or think they have the vaccine, go out and aren't taking the appropriate measures to take care of themselves.
The only thing is that everyone's informed that they either got a fake shot or a real shot. So they presumably would also know that chances 50-50 that they actually didn't get any kind of vaccine, right? Someone in the back had their hand raised or not? No? So why is that such a big difference? Bigger in the placebo-controlled group in the randomized designed experiment than in the other one? Yes?
Well, one idea was that we had said earlier that parents and families have a higher chance of getting the disease, and we said that people that can get are primarily from higher income families.
Mm-hmm.
So because those were all people who consented, then that would account for the higher number of cases for higher income people in that group.
Right. I think that's a good observation. So that is that we're looking in the randomized controlled comparison, we're looking at only consenters. And we had earlier mentioned that higher income parents are more likely to consent, and at the same time, their children are more likely to get the disease. So it does make sense that of the two different placebo groups, the placebo group from the randomized controlled getting the 71 per 100,000 is much larger than this control group because it's a different set of children. This control group, the observed one, has a mix of folks whose parents might consent and who would not consent. and the rate of getting polio for them is different. So then the question still is, this was extremely convincing to the medical profession that there's a real need to have trials, field trials that adhere to these notions of randomization, double-blind, using placebos, and but even still, there's another question here, and that is that you could play devil's advocate and say, well, let's just assume that the Salk vaccine actually is not effective at all, and that the kids who got polio would have gotten polio anyway, whether or not they got the salt solution or the actual vaccine. And it's just by chance that more of the kids who got polio got assigned to the fake treatment than to the real treatment. And so the only thing that we see going on here is just what might have happened by chance. The beauty of that is because we used a chance process, we can actually address that question. So, and you can't do that for the other question or for the other design. So the randomized design lets us answer this question to say, okay, we can play devil's advocate. There were 198 cases of polio in that group of about 400,000 children. Those kids were assigned at random to either get the Salk vaccine or to get the salt solution. It could have just happened by chance that so few kids who got polio were assigned to the vaccine group. And that's the only thing that's going on here. So it says it's only the randomization that led to 142 of the 198 sick children being assigned to the salt solution. And we can actually compute those kinds of probabilities. We can say, well, how likely is that? If there are 198 sick children, then there are 399,802 healthy children. And they're all in this big group of 400,000. So I've rounded the numbers a little bit. And 200,000 of them are going to be picked at random and given the vaccine. And the other 200,000 are going to be picked at random and given the salt solution. So what's the chance that when I do this split into the into the control group and the treatment group, what's the chance that this random chance process winds up with having 56 or fewer of the polio cases in the vaccine group? We can use R to figure this out. We can create our population of 400,000 children where we have 198 with polio and 399,802 without. That's what that first line of code is. There's the rep function. C10, remember, is a vector of ones and zeros, or of 1, 1, and 1, 0. The 1 is for the polio, and the 0 is for the healthy children. Then the next argument to the rep function says, how many 1s do you want and how many zeros do you want? 198 1s, 399,802 zeros. So polio pop is my population of children. There's 400,000 children that are going to be divided into two groups of size 200,000 each. And what I'm arguing is that they would have gotten polio anyway. So essentially, I know that in this group of 400,000, 198 of them got polio and the others did not. So I can take a sample with a sample function in R. So sample from the group called polio pop, sample 200,000. So what that does is it picks 200,000 of those 400,000 numbers at random without replacement from that whole group. And it assigns it to the variable called SAMP. And then if I add up SAMP, I'm adding up ones and zeros. And so the final thing will be the count of how many children in that group had polio. So that's essentially what went on in that field trial. Yes?
I just have a question about the actual trial. Like, how many times do they do it?
That's exactly what we're about to do. So they did it once. They got these 400,000 consenters, and they split them into these two groups, and it took a whole year and $17.5 million. So they could only do it once. But now that we've got the results, we can use a computer. In fact, they couldn't use a computer back then. This took, what I'm about to show you, you probably don't want to do on your computer. Mine's relatively new, and it still took about 20 minutes on my laptop to do this computation. So beware if you want to try this out. As I said, well, let's do it again and again and again and again, which is exactly what you're talking about. I did it 50,000 times. So I pretended that I ran this split into the treatment group and the control group 50,000 times. And so how many of those times did I get 56 or fewer kids in the control or in the treatment group? So there's a wonderful function in R called replicate. And it takes a clump of code and it repeats it however many times you want it to repeat. So the first argument of replicate says, do this many times, 50,000 times. Then in the curly braces, you put the code that you want to have done over and over again. So I'm going to sum up the result of sampling my polio population 200,000 times. So picking 200,000 from my polio population. And what I then did, after I did that, I then made a table of all of the counts. And I will show that, and I plotted it, and there it is. So let's read this. Let's read the axes. The x-axis is the number of sick children that wound up in my sample of 200,000. The y-axis is the count out of how many of those 50,000 trials did I get that many children that were sick. So in other words, the most popular was 99 or 98. So most often I got roughly split right down the middle, 98 or 99 children that were sick in my group. So where's 56? It's not there. In my 50,000 repeats, I didn't once get a group of 200,000 kids that had as few as 56 kids in it. The smallest was 72. So out of my 50,000 repeats, each time pretending I was doing the experiment, I never got even close to as few as 56 kids of the 198 sick kids in my group. We're going to be learning how to do this actual calculation in the next couple weeks. But the chance of getting so few children in a random assignment of picking 200,000 is less than 1 in a billion. So when faced with this chance, they concluded, overwhelmingly so, that yeah, that could have happened. That means there is a chance of 1 in a billion that there was absolutely no effect of the vaccine. But that was such an unusually rare event that instead they came to the conclusion that polio can be, or the vaccine is effective. And then if we go all the way back to, look at that histogram of the incidences of polio, you'll see that in 1954, 55, 56, the rates of polio started to decrease. That's when they came to the conclusion that the field trial was a success, that Salk's vaccine worked, and decided that all children should get vaccinated. All right, so we're not going to fast forward a few years, about 40 years, and then to last week, and look at 2 other clinical trials to say, this is all well and good. These, as I mentioned, that this field trial really was a sort of poster child for designing randomized controlled experiments in medicine where there would be double-blind subjects and evaluators. But there are all sorts of ethical dilemmas that also go hand in hand with this. And I want to show you two examples of that. To let you know, it's one thing to sit in a stat class at the university and say, oh yeah, now we get it, this really makes sense. And it's another thing to see what happens in actual practice. So in 1994, there was a huge news splash about how a doctor had falsified his data. And at first, when this story came out, it was just that the doctor had broken the protocols for a breast cancer experiment. And a lot of people's reaction was like, oh, what a monster this guy must have been. He was operating on women when he shouldn't have been. That's not what happened. Instead, he was breaking the protocols to help his patients. And so here's the story of Dr. Roger Poisson from the University Hospital in Montreal. He lost his job. The director of the National Cancer Institute here in the United States that was funding this study said that the doctor entirely missed the point of the potential harm to women all around the world that could have come from him tainting his data. So he supplied false information on 99 of his 1,500 patients that he had enrolled in a breast cancer study. What did he actually do? He had acknowledged 115 anomalies in his reporting. So there were 22 different rules in the protocol for enrolling women into the study. One of those rules was that the woman had to decide to join the study or not within 28 days of being diagnosed with breast cancer. And then the decision as to what treatment she would get would be made, et cetera. So in 54 of these 150 cases, he faked the data and he changed the date at which the diagnosis was made in order for the woman to be enrolled in it. And he did it for the patients that he thought really needed this new treatment. So he went and changed the dates so that they would be eligible to enroll because he thought that they would benefit from this latest method of treatment. So is that really a big deal? That's all he did? Yes? Mm-hmm. No, he had 1,500 cases over. So he had 1,500 cases over 15 years. He was one of several sites across Canada and the United States. And yeah, right. So, and of those, one of the things he did was for 54 of those women, he altered the date at which they were diagnosed with cancer so that they could be eligible to join the study. So is this really a big deal? There were 22 different rules. That's one of them. He only did it for 54 women, and he just fudged the date a little bit. I mean, they could have found out a little bit earlier or later. What's the big deal? He said that his irregularities were of a technical nature and did not affect the findings of the research. The head of the Cancer Institute says that the doctor has no understanding or respect for the scientific method. So hopefully you can see the tension here between these do seem like arbitrary rules, and the doctor is being faced with individual patients who are ill, and at the same time, there are all of these possible other factors that could affect the outcome and the decisions as to whether or not to proceed with a new kind of treatment or not. So here's one that's much more recent. In fact, it was in the New York Times last week. A new drug stirred debate on rules of clinical trials. So the news had found these two cousins, Thomas McLaughlin and Brandon Ryan, and they're from California. They essentially grew up together in the Central Valley, and they both developed melanoma at the same time a year ago. So in 2009, they learned that they had a lethal skin cancer, melanoma. The standard chemotherapy treatment was only effective for about 15% of the patients, and it extended their lives for about 2 months. There was a new drug that was being tested in a clinical trial, PLX 4032, and it was already in phase 1 trials. There are several phases of these clinical trials. In the phase 1 trials, it was shown that any 1% of the patients had reduced tumor growth for, on average, 8 months. And they were now in phase 2 trials. And in phase 2 trials, they were trying to answer the question, would this really help patients with melanoma live longer? The roll of the die was such that Thomas McLaughlin received the new treatment, and Brandon Ryan was randomly assigned to the control group, the chemotherapy group, even though, so here's, so the control group is the standard way of treating the disease. And the problem with this is a huge disparity in what's already seen as the effect of this new treatment. So the preliminary results were being presented at a medical conference, and this is some of the debate. Even among the medical profession, there's huge debate over what should be done. Dr. Chapman, the middle quote, is the one who's in charge of the study. Dr. Rosen says, "Excuse me, but if it was your life on the line, doctor, would you dacarbazine use, in other words, would you do the chemotherapy?" Chapman responded, "My goal is to find out as quickly as possible in as few patients as possible whether this works. If we never know, then we're never going to be able to build on anything." So you see the tension there. Dr. Fisher, who's a doctor at MIT, puts in his personal view is that this whole thing's nuts. I don't know anyone who hasn't shuddered at the concept that we can't let patients on the control arm cross over because we need them to die earlier to prove this point. A quote from the New York Times says that this Dr. Chapman, who's running this, has lived through many trials of drugs that have failed to live up to their early promise. Almost every oncologist knew of a case 20 years ago where it looked like bone marrow transplants were going to really help breast cancer patients. And a lot of people signed up for these bone marrow transplants. And it was then found out through clinical trial that, in fact, they were much less effective than chemotherapy, and in some cases caused death. So, unfortunately, Mr. Ryan, who was assigned to the control group, died in June 2010, and his cousin is still alive and has received this treatment for 9 months. What's really interesting, though, with this particular case is that what's going on here is that the practice of medicine, or the drugs that are being created now, are changing, are so different than the drugs that were like the polio vaccine from 50 years ago. And so now it's being reopened, the question of whether a controlled trial is still the best method for evaluating the effectiveness of these new genetically targeted cancer drugs. And so the critics are arguing that the new science behind the drugs means that the old rules need to change. Dr. Sawyer says that this could be one of those defining cases that says our system has to change. So what Jonas Salk and Tommy Francis put together in the 1950s, maybe at this point, given the kind of medicine that is being developed, is out of date. So one of the heads of the FDA says that the new wave of drugs in development, especially for intractable cancers, might require individual evaluation. That's very different from taking a huge group of people and randomly assign them to one thing or another. So I'm going to end on this one note, is this debate is very closely linked to the On the Same Page program. For those of you who are freshmen here, you're well aware of it, and maybe those of you not, because it's received so much attention in the press. So this is all about personalized medicine. A couple weeks ago, Jasper Ryan, who's the feature person, gave a talk on looking for the good news in your genome. I highly recommend that you see the next featured speaker on personal genomics and public angst, Wednesday, September 29th. That's next week, Wednesday. And if you go to Professor Charo's talk and want to write up a one-page paper about what you learned from that talk, you may get extra credit for this course. See you on Friday.